Hi, I'm Lars Hof from the University of Groningen. In this work, we perform system identification and experimentally compare tracking controllers that use only position measurements. Our platform is a Quansor 2-link manipulator with brush DC motors and encoders. The controllers we test assume torque inputs, but the hardware is voltage driven. So we identified the motor parameters and implemented a feed-forward plus proportional current controller that lets us command joint torques directly. We then identified the robot dynamics using the inverse dynamic identification model with ordinary least squares, estimating 5 lumped inertial and frictional parameters from 10 excitation trajectories. With this model, we implemented 3 position-only controllers: Ferguson 2025, using a port Hamiltonian observer with input to state stability guarantees; Rascon 2020, a filter-based feed-forward proportional integral structure; and Cruise 2021, which adds saturation for finite time tracking. All controllers were tuned to the onset of oscillation. Next, I'll show our experimental setup in more detail. So the arm is controlled from Quark, which is a software developed by Quansor and is run in Simulink. This allows for real-time control and monitoring of the performance. We currently have a simple tracking experiment running. The signals from Simulink are sent to the Quansor board, which we can find here, which is connected to the motherboard of the computer. And the Quansor board then has different signals. It has analog signals, which it will send to the power amplifier, which will amplify those signals and send them to the motors. Next to that, there are also digital signals sent to the various encoders on the arm to read back position and current in the motors. We also have a custom calibration station to calibrate the motors in the Quansor arm. Currently it's not set up, but I will quickly explain it. So in here we have 2 motors. If we disassemble the arm, we can then put the motors together with the gearboxes on this station and connect the shafts of the motor and the torque sensor. And then the torque sensor will measure the torque as the difference between the load on the motor side and loads that is applied here. So here you can hold the load to press an arbitrary load on the motor. And how the signals are measured is through a Teensy. Teensy is a small microcontroller similar to Arduino, and this is connected through various cables to the Quansor digital board. Then in Simulink we send a digital pulse signal, which will request a measurement at each time step of the simulation. And Teensy will then, when the signal occurs, send the signal to the PCB to actually make a reading from the torque sensor. And the torque sensor is through this cable then connected to the PCB board. Here we perform a tracking experiment. In all plots you can see reference and measured signals of, on the left hand side, joint positions, and on the right hand side, the motor current.